Good day everyone. Welcome to another edition of Class Vice Primary School online chemistry class. I'm Solomon, your online chemistry teacher. Now in our lecture today, we'll be talking about sulfur and its compound. Now under sulfur, we're going to talk about its occurrence in nature, electronic configuration, how it can be extracted, physical and chemical properties. And after that, we're going to discuss some important uses of sulfur. And after that, we're going to study or look at some important compounds of sulfur. Sulfur is a non-metallic element and the second member of the chalcogen family. Now, the chalcogen family are the group 6 elements on the periodic table. Now, the other members of the family include oxygen, selenium, tellurium, polonium. Now, sulfur has been known for its medicinal value, but its chemical nature was discovered in 1789 by Lavoisier when he discovered it as an element. Sulfur makes about 0.1% of the Earth's crust. It occurs freely at the deposits in USA, Poland, Japan, and New Zealand. It often accompanies volcanic eruption. In volcanoes, sulfur have been formed by the incomplete combustion of hydrogen sulfide in the volcanic gases. It also exists in its combined state as sulfide, tetrasulfate 6 acid, and also tetrasulfate 6 salt, and in organic compounds like some proteins. The electronic configuration of sulfur. Now, the atomic number of sulfur is 16, and the electronic configuration, as you can see here, is 1s2, 2s2, 2p6, 3s2, 3p4. Now, as you can see, that means sulfur has 3 shells. As you can see in this diagram, this is the first shell, the second shell, and the third shell. Now, from the electronic configuration, you can see that sulfur has 6 electrons in its outermost shell. Now, the outermost shell is the third shell, and that is the 3s and the 3p, and they have the 2 electron and 4 electron respectively. And when you sum up the total number of electrons, that's 2 plus 4, that's 6. And if you count it, that's 1, 2, 3, 4, 5, 6. Now, from this electronic configuration of sulfur, you can conclude that sulfur need just only 2 electrons to attain the octet structure of the nearest noble gas. Now, it accomplishes this by undergoing either electrovalent combination, which is also known as the ionic combination, with metallic elements like sodium and calcium and potassium, or by undergoing covalent combination, which is sharing of electrons with non-metals and also with itself. Non-metals like oxygen, for example. And to the extraction. Now, sulfur is extracted industrially by what we call the Frasch process. Now, in this process, 3 concentric tubes are sunk to the bottom of sulfur deposits. I told you that sulfur is deposited as a raw material in USA and in Poland. Now, after we've passed these tubes, the 3 concentric tubes, into the sulfur deposit, then superheated water at a temperature of 160 degrees Celsius and a pressure of about 18 atmosphere is forced down the outer tube. Now, let me show you a picture of what I'm saying. Now, this is just a picture illustrating the extraction of sulfur. Now, as you can see, this is the rock containing the sulfur. Now, these are the tubes, the 3 concentric tubes. And this is the first, the second, and the third. As you can see, the outlet of each of the tubes. Now, the superheated water of 160 degrees Celsius and at a pressure of 18 atmosphere is passed into this first outer tube, which then dissolve the solid sulfur, the solid form, this forming a liquid form of sulfur. Then after that, hot compressed air is passed through the second tube, which is the middle one, the second tube, which is at the middle. Hot compressed air Let's take note of that. Hot compressed air is passed through the second tube. As you have here, as you can see, the compressed hot air is passed down the central tube. Now this causes a decrease in the pressure and thereby forcing the liquid sulphur to come out through this third tube. Now the superheated sulphur melts the solid sulphur, forming the liquid sulphur. Then hot compressed air is passed to reduce the atmospheric pressure, thereby causing the liquid sulphur to move up to the third tube. Now, in the extraction of sulphur, the physical property employed is melting point. We consider the melting point of sulphur. So that means we consider the way the temperature at which the water is heated is considered to be able to increase the temperature of sulphur up to its melting point that will cause it to melt. Then after that, now this is actually different from when we are extracting nitrogen. Now nitrogen we consider boiling point. In the industrial preparation of nitrogen we consider the boiling point, but here for sulphur we consider the melting point. Let's take note of that. As for the physical property of sulphur, now sulphur is a yellow solid and it exists in two major forms, majorly, which are the amorphous and the crystalline. We also have a third form, the plastic sulphur. Now from our SS1 we know that when an element exists in different physical states, that's what we call allotropy, right? Now sulphur exhibits allotropy. To the second property, it is insoluble in water but soluble in carbon 4 sulphide and methylbenzene. And we know that methylbenzene is toluene. Now being a non-metal, sulphur is a bad conductor of heat and electricity. Sulphur does not conduct both heat and electricity. Also the density of sulphur depends on the allotropic form of the sulphur we are viewing. And sulphur has a melting point of 119 degrees Celsius and a boiling point of 444 degrees Celsius. That's quite high. Now to the allotropes of sulphur. I told you that allotropy is the ability of an element to exist in different physical form, right? To exist in different physical form in the same state. Different physical form but in the same state. Now also carbon also exists, also exhibits allotropy. Now you have the crystalline form of carbon, and under the crystalline form of carbon we have the diamond and we also have the graphite. If you check our videos under carbon, and also we have the amorphous form of carbon, and the amorphous form of carbon we have soot, we have charcoal, right? Now to sulphur, under the crystalline form of sulphur we have the rhombic sulphur and the monoclinic sulphur. Now the rhombic sulphur is also called the alpha sulphur, while the monoclinic sulphur is called the beta sulphur. Now the second allotrope of sulphur that we have is the amorphous sulphur. Now the third one is the plastic sulphur. Now the plastic sulphur, why we have the plastic sulphur, because this plastic sulphur does not behave like a crystalline form of sulphur or like the amorphous form of sulphur. Now please take note, rhombic sulphur and monoclinic sulphur are under the crystalline form of sulphur. Now rhombic sulphur. Now free sulphur, that means the normal sulphur that we have in our as a raw material, as deposits in raw materials, exists as rhombic sulphur in nature because it is the only stable allotrope of sulphur at a temperature below 96 degrees Celsius. And I'm sure that you are aware that room temperature, which that means the normal temperature that we have, the atmospheric temperature, is between 25 degrees Celsius to 29 degrees Celsius. Now that's why rhombic sulphur is normal, so the free sulfur that we have naturally, the natural occurring sulfur exists as rhombic sulfur. Now, crystals of rhombic sulfur are bright yellow and octahedral in shape. Now, they are made up of S8 molecules. Now, each S8 molecule consists of a ring of 8 atoms of sulfur. 8 atoms of sulfur. Now, rhombic sulfur is prepared by allowing a saturated solution of sulfur in carbon 4 sulfide to evaporate slowly. And after that, octahedral crystal will gradually be deposited. Now, I'll show you a picture of rhombic sulfur in our coming slides. Now, monoclinic sulfur. Monoclinic sulfur is obtained by melting sulfur in a crucible and allowing it to cool down slowly. Now, a thin crust will be formed on the surface of the crucible, and the crust is pierced with 2 holes to pour out the remaining liquid. Now, when the crust is removed, there will be a deposit of long, transparent, needle-like crystal of monoclinic sulfur. And this monoclinic sulfur, it is soluble in carbon 4 sulfide, and it is the only stable allotrope of sulfur between 96 degrees Celsius and 119 degrees Celsius. That means above 96 degrees Celsius, rhombic sulfur will change to monoclinic sulfur. Now, below 96 degrees Celsius, monoclinic sulfur will change back to rhombic sulfur. So 96 degrees Celsius is called the transition temperature for the crystalline form of sulfur. For the crystalline form of the transition temperature for the crystalline forms of sulfur. Now, above 96 degrees Celsius, you have the monoclinic sulfur. Now, below 96 degrees Celsius, we have the rhombic sulfur. Now, and again, monoclinic sulfur is amber in color. While rhombic sulfur is yellow in color. Yeah, it has a color of yellow. It is yellow in color. Now, this rhombic sulfur, as you can see, is octahedral in shape, and this monoclinic sulfur. Now, this is the transition. Above 96 degrees, you have the monoclinic sulfur. Below this should be below 96 degrees Celsius. Below 96 degrees Celsius, you have the rhombic sulfur. Now, to the amorphous form of sulfur. Now, amorphous sulfur has no regular crystalline shape from the word amorphous. Amorphous is anything that does not have a regular shape. For example, the amoeba in your biology. It is prepared as a yellow, almost white deposit when hydrogen sulfide is bubbled through water for a long period of time, and the saturated solution is exposed to air. And also, it is also observed in chemical reactions. Most of the sulfur you observe as deposits in chemical reactions, they're actually amorphous form of sulfur. And this is the equation you can see for the formation. Hydrogen sulfide being oxidized by oxygen and forming a deposit of sulfur, and also forming water molecule. And don't forget that sulfur is not soluble in water. Now, to plastic sulfur. Now, plastic sulfur is a supercooled form of sulfur. Now, if yellow sulfur is heated and poured into cold water, it will roll up into yellow ribbons, which look soft and elastic and will not dissolve in carbon 4 sulfide. Now, plastic sulfur is not considered to be a true allotrope of sulfur because it changes to rhombic sulfur on standing, and that's why it's not considered as a true allotrope of sulfur. And if you check when I was talking about the physical property, I did include plastic sulfur, but when I wanted to discuss the allotropic form of sulfur, I had to put plastic sulfur, but it's not generally considered as a true allotrope of sulfur. Now, let's talk about the effect of it on sulfur. Now, when sulfur is heated in a limited amount of air, it melts between the temperature of 115 degrees Celsius and 119 degrees Celsius, right, into an amber colored liquid, which is what the color for monoclinic sulfur. That means it is already monoclinic sulfur at that temperature. Now, when you continue heating that liquid, the liquid darkens as the temperature what increases. Now at about 160 degrees Celsius, the liquid become very dark and turns viscous. Now that means when you are heating sulphur and when you get to a temperature of about 160, when the sulphur actually gets to about 160 degrees Celsius, it begins to turn viscous. Then it reaches its maximum viscosity at 200 degrees Celsius. That means it turns viscous completely at 200 degrees Celsius. Now on further heating, it begins to flow again and boils to give a brown sulphur vapour at its boiling point of 444 degrees Celsius. Now when this vapour is condensed on a cold surface, a fine powder which forms a floral pattern is obtained. Now this floral pattern of sulphur is called flower of sulphur from the word flora. Now when we talk about flora, we talk about flowers. Now molten sulphur is often poured into tubular mold to form rolls of sulphur. You don't actually do that. But what we are just talking about is I want you guys to know the temperature at which sulphur begins to turn viscous and at when it attains its maximum viscosity. That is very important. Now to the chemical properties of sulphur. Now first, reaction with metals. Now sulphur combines directly with many metals to form sulphide when heated in the absence of air. But reactive metals like sodium and potassium combines with sulphur without heating if they are in finely divided form. That means when you have a solid sulphur and you have a solid sodium, when you grind them into powder, the sulphur and the sodium can react directly without heating. Now this is iron reacting with sulphur to form iron 2 sulphide. Now reaction with oxygen. When sulphur is heated in air, as we all know, oxygen is the component of air that causes combustion. Now when sulphur is heated in air, it burns with a bright blue flame to form sulphur 4 oxide. And this is the equation: sulphur plus oxygen to form SO2, which is sulphur 4 oxide. Don't forget, sulphur burns with a bright blue flame in air. Now reaction with copper. Sulphur reacts with carbon to form a colourless liquid which is known as carbon 4 sulphide. Now carbon 4 sulphide vaporizes readily to form a poisonous and a highly flammable fumes. Now that's why the preparation of carbon 4 sulphide is always done in fuel cupboards, and that's why fuel cupboard is used to prepare gases that are very poisonous like chlorine and also hydrogen sulphide. And when we get to hydrogen sulphide, we'll talk about that. Now this carbon reacting with sulphur to form the carbon 4 sulphide. This is actually very poisonous when it changes to gas. Now reaction with hydrogen and other non-metal. Sulphur reacts with hydrogen at high temperature to form hydrogen sulphide. And it also reacts with non-metals like phosphorus to form their respective sulphides. And this is sulphur reacting with hydrogen to form hydrogen sulphide. It can also react with fluorine to form with phosphorus to form the sulphide of phosphorus. Another non-metals also. Now reaction with oxidizing agents. Now sulphur is readily oxidized to sulphur 4 oxide when warmed with concentrated tetrasulfate acid. But when warmed with concentrated triazonitrate 5 acid, it is oxidized to tetrasulfate acid. Now when sulphur is warmed with concentrated tetrasulfate acid, it is oxidized to sulphur 4 oxide. As you can see in this equation, this is sulphur reacting with concentrated tetrasulfate acid. Now this formation of sulphur 4 oxide. Also the tetrasulfate acid is reduced to sulphur 4 oxide. But when we are using triazonitrate 5 acid, concentrated triazonitrate 5 acid, the sulfur is oxidized to tetrasulfate 6 acid, while the trinitrate 5 acid is reduced to nitrogen 4 oxide, as we have in this equation. Now this trinitrate 5 acid being reduced to nitrogen 4 oxide. Now this sulfur being oxidized to tetrasulfate 6 acid. Now reaction with hot concentrated alkali. Now what are alkalis? Alkalis are we have example of alkali, we have the sodium hydroxide and we have the potassium hydroxide. Now sulfur will react with hot concentrated alkaline solution to form a mixture of sulfide and triazosulfate 4. Now in the presence of excess sulfur, okay, let's first talk about the formation of the sulfide and the triazosulfate 4. Now this sulfide, this is just an ionic equation. Take note, this is an ionic equation. Now this sulfur reacting with the hydroxide ion from the alkali to form a sulfide, metallic sulfide, probably sodium sulfide, and also a triazosulfate 4 salt, probably sodium. Let's assume it is sodium. Let's assume the alkali is sodium hydroxide. So we have, if it's sodium hydroxide, we have sulfur plus sodium hydroxide to form the sodium sulfide and also the sodium triazosulfate 4, and also forming some water molecule. Also, it can be also potassium. Then you just put it like that. But when the sulfur is in excess, the sulfide will form a polysulfide and the triazosulfate 4 will form a triazotiosulfate 6. Now, the sulfide will react with the excess sulfur to form a polysulfide, and the triazosulfate 4 will react with the excess sulfur to form the triazotiosulfate 6. Now, please take note that this N that you can find here only ranges from 1 to 8. Anything above 8 is not visible. Now to the uses of sulfur. Now sulfur is used in the vulcanization of rubber. Now you talk about vulcanization of rubber when we are discussing organic chemistry. Now sulfur is also used in the preparation of tetrasulfate 6 acid, which is an important chemical in the laboratory. You know, we use tetrasulfate 6 acid as a drying agent and also as a dehydrating agent. Now, also sulfur and some of its compounds are used as fungicides and production of skin ointment. Now, this is just a practice question for you guys, and this is where I'm going to stop today on our lecture on sulfur. Thank you for watching this edition of School Advice Secondary School Online Chemistry class. And you can contact us on our website at www.schooladvisorsecondary.school.com, or check your group if you have any questions and drop it on your class WhatsApp group. Thank you.